Good morning. Good morning. We will continue with the discussion on transformer. There are few more types of problems based on the calculation of efficiency. So let us solve one more problem which is of important nature. A 250 kVA single phase transformer has percentage efficiency 98.135 at full load and 0.8 power factor lag and percentage efficiency 97.751 at half load and 0.8 power factor lag. Find iron loss and full load copper loss. Also find percentage efficiency at 3/4 load at 0.6 power factor lag. So this is a typical problem wherein the efficiency of the transformer at full load 0.8 power factor has been given as 98.135. At another load, namely half load 0.8 power factor lag, efficiency is 97.751. So using this data, you have been asked to calculate iron loss and full load copper loss. So we have to use this formula which we have already studied in the previous class. Efficiency of transformer at X times load, full load, and power factor cos phi given by X times kVA into 10 raised to 3 cos phi by X times kVA into 10 raised to 3 cos phi plus X square times WC plus WI, where WC is full load copper loss, as already we have studied. WI is iron loss. So from first data you need to substitute from the data at full load x equal to 1 and power factor 0.8, efficiency is 0.98135 equal to, that is efficiency is 0.98135 equal to x. X is full load. Full load means 1, kVA rating 250 into 10 raised to 3 into 0.8 divided by 1 into 250 into 10 raised to 3 into 0.8 plus x is 1, WC is unknown to be calculated, WI is to be calculated. Okay. So like this, from the given data for the first case, we have written the efficiency in this way. You can isolate or calculate WC and WI like this, wherein on simplification you will be getting the equation as 0.9851 WC plus 0.98135 0.98135 WC plus 0.98135 WI equal to 3730. This is equation A. So in terms of WC and WI, we have got this equation. On cross multiplication, you find this equation. Similarly, using the second data, we will create one more equation in terms of WC and WI as follows. The other efficiency is 0.9751 equal to half load, that is at half load and power factor 0.8. That is second case. Efficiency has been this much. Substitute in place of x, we need to substitute half because it is half load. kVA 250 into 10 raised to 3 into cos phi, that is 0.8 divided by half into 250 into 10 raised to 3 into 0.8 plus x squared, that is half squared, WC the unknown and WI. So using this substitution, once again cross multiply the terms and get another equation in terms of WC and WI as 0.2443 WC plus 0.97751 WI equal to 2249, which let us call it as B, equation A and B. So, two simultaneous equations in terms of WC and WI have been created. Now, using A and B, solving for WC and WI. From equations A and B, solving for WC and WI. You can use your calculator for solving these equations. Readily you will get the answer. So please look into the formalities to solve the equations A and B directly in your calculator. So on doing that, you will get the answer readily as WC equal to 2000 watt and WI 1800 watt. 1800 watt. So in this way, we have got the values of the full load copper loss. This is full load copper loss and this is iron loss. Now you can use these values for calculation of efficiency at any load and power factor. Because you know this WC and WI. Okay? So therefore, to find efficiency at 3/4 load and power factor 0.6. In the last part of the problem, this is the question. Okay? X is 3/4 and power factor is 0.6. Once again, using the same formula, you will be calculating the efficiency equal to X 3/4 250 into 10 raised to 3 into 0.6 divided by 3/4 into 250 into 10 raised to 3 into 0.6 plus x squared 3/4 squared into WC 2000 and WI 1800. So, by using the values of WC and WI, substitute and calculate the efficiency at the 3/4 load and power factor 0.6. So, please complete this calculation as a homework, that is efficiency at 3/4 load and 0.6. So, this is another type of problem that you can refer. Now let us go ahead with some additional information on the efficiency, which often we require in some objective type of questions. Just make a note. Maximum efficiency occurs when copper losses equal to iron losses. That is, maximum efficiency occurs when copper losses become equal to iron losses. That is, so at any load, copper loss is given by x squared times WC. Iron loss remain constant as WI. So therefore, what you find is x equal to x squared equal to wi by wc. X is equal to wi by wc under root. That is, at a fractional of the full load, at a fraction of the full load, that is x, at this fraction of full load, maximum efficiency occurs. At this value, x equal to this, you will find the occurrence of maximum efficiency. Okay? So in general, for our purpose, for the first semester level, just try to remember whenever variable losses, copper losses become equal to the constant losses, that is iron loss, maximum efficiency occurs. So this much information just bear in mind. So at the end we will solve one more problem on voltage regulation. Okay. So just note a problem on voltage regulation. Example, a 5 kVA 200 volt bar 100 volt single phase transformer has rated secondary voltage on full load, when the load is removed means reduced, load is removed, secondary voltage, the secondary voltage becomes 110 volt. Determine percentage voltage regulation of the transformer. Okay. So as you can see here, this is a transformer. This is primary supply 200 volt. This is the secondary, that is 100 volt, that is Vs. This is Vp. Vp is 200, Vs is 100 volt. So whenever there is a load, full load, at full load, this voltage is 100 volt. At full load, this voltage is 100 volt. On removing this load, the transformer will attain no load condition. The load has been removed. Therefore, voltage tends to increase, and it has increased to 110 volt. So with this information, you are supposed to calculate the voltage regulation. Okay. So from data, we have secondary voltage at full load. Secondary voltage at full load is 100 volt. Secondary voltage at no load is 110 volt. 110 volt. So one general aspect you need to remember, that is, this 100 volt is the rated voltage. Primary voltage rated value is 200. Secondary voltage rated value is 100. So whenever we calculate the regulation, in the denominator of the formula, it is advisable to substitute the standard reference value as percentage voltage regulation equal to VSNL minus VSFL divided by divided by, it is better to use in this particular problem VSFL because rated value is 100. That value you need to use. That is always advisable in this case. So accordingly, we can calculate. So substitute 110 minus 100 divided by 100. 10%. That is 10 divided by 100. Into 100. That is 10%. 10%. Okay. So like this, in this problem, this formula is to be used. Even if you write here VSNL and calculate, you will get the credit. Okay. But in practice, this we have to note and follow. In practice, the voltage regulation should be between 5 to 10% only. 5 to 10% only. If there is a transformer with some 30% voltage regulation, it is not a good transformer. It is not a good transformer. So that just concern. And it is worthwhile to know why this voltage regulation occurs. So in this transformer, this is electromagnetic machine. It has got primary winding, secondary winding. So therefore there will be primary resistance. There is resistance for the primary winding and secondary winding. There is leakage reactance for primary winding and secondary winding. Okay, so resistance is R and leakage reactance let us indicate by X or XL. So there is presence of two parameters in primary and secondary winding, that is resistance and inductive reactance. So whenever the transformer is loaded, supply is given, secondary voltage appears, load is connected, then you will find the flow of current, secondary current IS and primary current IP. So whenever current flows in the transformer through the resistance R and leakage reactance XL, there will be a voltage drop IR and IXL. Due to this voltage drops, a part of the voltage reduces. With increase in load, current increases. With increase in current, the drops increase. And whenever the voltage drops increase, the terminal voltage definitely decreases. So therefore, the terminal voltage decreases due to the resistance of the transformer and leakage reactance of the transformer. Okay? So this fact you can easily understand. Let us conclude the discussion on transformer by quickly looking at applications of transformer. So as we have seen in power systems, there is generating station, generator, generating power at 11 kilovolt. This power is to be transmitted over long distances from generating station to load. So for example, Belgaum is load, we are the consumers. Generating station is located in some project, say Kali project, Bikanagar, Dandeli. So from there, over 150 kilometers distance, the power has to come from the generating station to load in the present case. So over this long distance, the power, electric power has to be transmitted. For that purpose, as we have studied in the first topic, while studying the single line diagram for the power systems, we have seen that this voltage has to be stepped up, increased to some higher value of the order of 220 kilovolt. In our region, we are using 220 kilovolt. In some regions, they have used 400 volt, 750 kilovolt, and so on. Okay, so voltage has to be increased from 11 kilovolt to 220 kilovolt. So for that purpose, we need a transformer, that is a step-up transformer. So for increasing the voltage in this case at the generating station, a transformer is required. In the load, the level of the voltage has to be reduced to the extent of 440 volts 3 phase or 230 volt single phase. So in the rear end of the power system, at the domestic level, the voltage has to be reduced. So the 220 kilovolt voltage has to be reduced. First it is reduced to 11 kilovolt in the first stage. Then later, once again, one more transformer we have to use to further reduce the voltage from 11 kilovolt to 440 volt. Okay. So in the rear stage, we need step down transformers. Step down transformers. Okay. So prominently, we need the transformers in the power systems, which are the integral parts of any power system. So that is the primary application of the transformers. Then when we come to the domestic applications, whenever we are using the electronic devices like say TV, tape recorders, some machines, domestic machines and tools, the voltage has to be reduced from 230 volt to 24 volt or 12 volt or 9 volt as per the requirement. So the reduction in voltage has to be done. So for that purpose, we use small step down transformers, very commonly in all electronic equipment. So that is another the application of the transformers. Okay. So through the discussion of this applications of transformer, we have come to an end on the discussion on transformers. And the most important point, one more point, then we conclude. Very important aspect. Transformers are used only in AC circuits. You should not apply DC. Should not apply DC to a transformer. We should not apply DC supply to the transformer. If you apply DC supply to the transformer, it burns readily. It burns readily because the transformer, if you apply AC supply, whenever you apply VP, there is production of self-induced EMF in the primary, which is opposite to VP. So the current drawn by the transformer will get limited automatically with AC supply because there is production of EP. EP is produced only when AC supply is given. If you give DC supply, there will be no change in flux linked with the primary. There will be no self-induced EMF, that is, EP will remain 0. Therefore, there is no opposing voltage with respect to VP, and with large value of VP, large amount of current will flow into the primary winding, and therefore the primary winding will get burnt, damaged. Therefore, we should not use the transformers in DC circuits. Okay? So, thanks for your patient listening.